Hello geometry students, welcome to this two-part lesson. We're going to be talking about angles of a polygon and then also an introduction to parallelograms, a topic we'll spend a couple of days on. So the first thing we're going to talk about is the sum of the measures of the interior angles of a polygon. And so we're going to end up eventually with a theorem that gives us a formula for finding out the sum of the measures of the angles of the interior angles of a polygon. But to get there, let's see if we can derive this formula. So the first polygon I want you to look at is a triangle. Now, as you know, a triangle has three sides, okay? And this column, let's not worry about just yet when we're talking about triangles. We'll be talking about diagonals in just a minute and creating triangles with a diagonal, but there are no diagonals of a triangle, so there's just one triangle. And as we know, we've proved last semester that the sum of the measures of the interior angles of a triangle is 180 degrees. So now let's take a look at this quadrilateral. Quad means four, so the number of sides of a quadrilateral is 4. And so what we're going to do is we're going to choose one vertex, and then what we're going to do is draw all possible diagonals from one vertex. So let's just choose this vertex. And if I draw a diagonal, now what a diagonal is it's a segment whose endpoints are non-consecutive vertices. So we can see that these two vertices are not consecutive, as in these two vertices are consecutive. So if I connect two non-consecutive vertices, we have what's called a diagonal. That's why a triangle has no diagonals. There's no way I could connect two non-consecutive vertices from one vertex. But anyway, back to our quadrilateral. When we do that, when we draw that one vertex that one diagonal from one vertex, we've now created two triangles. So if we want to think about the sum of the measures of the interior angles, well, now that we have two triangles, we would take 2 times 180 for a total of 360 degrees. So the sum of the measures of the interior angles of a quadrilateral is 360. Now let's repeat this process with this pentagon. So again, we're going to pick one vertex. So I'm going to pick this vertex and I'm going to draw all possible triangles. So when I do that, well, first of all, let me back up and say that this pentagon has 5 sides. Has 5 sides. When I draw all possible triangles from one vertex, it creates 1, 2, 3 triangles. So now if we wanted to total up the measure of all the interior angles, we would take 3 times 180, which turns out to be 540 degrees. Okay, let's do that one more time, and I think we'll be able to see the pattern. So now let's take a look at this hexagon, which has 6 sides. Okay, so again, pick one vertex and draw all possible diagonals from one vertex. And you can see that when we do that, we create 1, 2, 3, 4 triangles. Okay, so there's 4 triangles. Whoops, 4 triangles. So if we want to get a total for the measures of the interior angles, we would take 4 times 180, which turns out to be 720 degrees. Okay, so I think you can kind of see the pattern here. You'll notice if you look at this column and this column, you'll notice that the number of triangles created when we draw all diagonals from one vertex, this number of triangles is always 2 less than the number of sides. And then when we try to get the sum of those interior angles, we take 2 less than the number of sides and we multiply it times 180. So in other words, in general, if we have a polygon that has n sides, if we were to draw all possible diagonals from one vertex, there would be n minus 2 triangles. So to get the sum of the measures of the interior angles, we would take n minus 2, the number of triangles, times the total of interior angles of one triangle, which is 180, and that would give us our total, or our sum of the measures of the interior angles. So that leads us to our interior angle sum theorem, which says the following. It says the sum of the measures of the interior angles of an n-sided convex polygon would be n minus 2, that's the number of sides, minus 2 times 180 degrees. Okay, so we're going to take a look at some examples in just a second, but real quickly, I just want to refer you to this chart. These are some terms that you probably already know, most of them, but get familiar with the names of these polygons. We name a polygon by the number of sides that it has. Okay, so let's take a look at this first example, which says, find the sum of the measures of the interior angles of a convex heptagon. Well, we can see over here that a heptagon has 7 sides. So since it has 7 sides, we'll use this interior angle sum theorem, take the number of sides minus 2 and multiply that by 180. So we're going to take, heptagon has 7 sides, so we'll take 7 minus 2 and we'll multiply that by 180. So some quick arithmetic, we can see that our final answer is 900 degrees. Okay, let's take a look at another example. This one says, find the measure of each interior angle of quadrilateral ABCD. Okay, so this quadrilateral, it has 4 sides. Notice we already know half of our answer. It says find the measure of each interior angle. Well, 2 of those angles are right, so we already know that the measure of angle B is 90 and the measure of angle C is 90. So to find A and D, those measures, we need to figure out what X is. So to find X, we need to write an equation. Well, since this polygon has 1, 2, 3, 4 sides, I know that the total, the sum of the interior angles would be 4 minus 2 times 180, which turns out to be 360 degrees. So I know that all 4 angles total 360 degrees. Well, let's go ahead and simplify this a little bit. If B and C both have a measure of 90, we can go ahead and subtract 180 from 360, which gives us 180 degrees. In other words, the 4 angles total 360. We know 2 of those 4 angles total 180. So these 2 angles, X and 3X, would total 180 degrees. So let's go ahead and write an equation. 3x plus x totals 180 degrees. Let's go ahead and figure out what x would be. So I'm going to combine like terms, divide both sides by 4, and x turns out to be 45 degrees. We go ahead and say 45 degrees because we can see that this angle here is x. So now to answer the question, it says find the measure of each interior angle. So let's just make a list. We know that the measure of angle A would be 3 times x. That's 3 times 45 degrees, which is 135 degrees. Okay. The measure of angle B is one of those right angles, so it's 90 degrees. The measure of angle C is the other right angle, so it's 90 degrees. And then the measure of angle D is x, okay, and we found out that x is 45. So the measure of angle D is 45 degrees. And then if you wanted to check, I suppose you could go ahead and just add up these 4 measures, and they should total 360 degrees. Okay, now let's take a look at example 3, which says, find the measure of each interior angle of pentagon HJKLM. All right, so we can see that this is a pentagon. It has 5 sides. So since it has 5 sides, we know that the sum of the interior angles would be 5 minus 2 times 180, which turns out to be, let's see, 540 degrees, okay? So to find the measure of each of these angles, we need to know what x is. So what we'll do is we will total all 5, the measures of all 5 angles, and we know that that total is going to be 540 degrees. So in other words, I'm going to start with H. Its measure is 2x, plus the measure of J is 142, plus the measure of K is 2x, plus the measure of L is 3x plus 14, plus the measure of M is another 3x plus 14, and the sum of the measures of all 5 of those angles we know to be 540 degrees. All right, so now it's just an algebra. We need to gather up our like terms. If we add up all the x terms, that's going to total, let's see, 10x. And then when we add up our constant terms, 142 plus 14 plus 14 totals 170. So 10x plus 170 is equal to 540. And so now we'll just simply solve this for x. So you get 10x is 370, so x is 37. So now that we know what x is, now we can write the measure of each angle. So let's just make a list. We know that the measure of angle H, let's see, H is 2x. 2 times 37 would be 74 degrees. Okay, so that's H. The measure of angle J, oh, we already knew that one. That's 142 degrees. Oops, 142 degrees. Okay, the measure of angle K is, let's see, K is 2 times 37, so that's 74 degrees. 74 degrees. Okay, the measure of angle L is equal to 3 times 37 plus 14. All I'm doing is I'm just putting, remember x was 37, and I'm just putting a 37 in for x, so that's 3 times 37 plus 14, and that is equal to 125 degrees. And then we don't need to do that work again. Notice that L is also 3x plus 14. So the, not L, excuse me, I'm talking about M now. M is also 3x plus 14. So that angle then, the measure of angle M, is also 125 degrees. Now let's take a look at example 4, which says, find the measure of each interior angle of the regular, oh, I left a word out, regular. Well, if you were to count the sides of this polygon that appears on the face of a Susan B. Anthony $1 coin, you would count and see that it has 11 sides, and the name of a 11-sided polygon is a handecagon. So I left that word out, sorry about that. So we're going to find the measure of the regular handecagon that appears on the face of the Susan B. Anthony coin. All right, so, oh, and notice what we're actually asked to find here. Find the measure of each interior angle. So what we're going to do is we're going to find the total measure of the interior angles. Well, we have a formula for that. If we take the number of sides minus 2 and multiply that by 180, that's going to give us the sum of all 11 of these angles. Now, since this is a regular polygon, that means all 11 of these angles measure the same. So if I take that total and divide it by 11, that's going to give us the measure of one interior angle. So if I simplify that numerator, it turns out to be 1,620. So we'll take that 1,620 degrees and divide it evenly among the 11 angles, and it turns out to be 147.27 with that 27 repeating degrees. We might want to instead write it as a fraction. 147 and 3/11 degrees would be the measure of one of those interior angles. Okay, and then let's take a look at example 5, which says the measure of an interior angle of a regular polygon is 135. Now this one's asking us find the number of sides in the polygon. So we don't know how many sides that polygon has. We just know that the measure of each interior angle is 135. It's regular, so they're all the same. So let's just write an equation and see if we can figure this out. Okay, 135 degrees is the measure of one of those angles. Well, to find the measure of one of those angles, we'll take the total of the interior angles, which would be n minus 2 times 180. Okay, that, what I've written right here, is the total of all n angles. What we're going to do now is divide that total by the number of sides, which is n, and when we do that, we get 135. Okay, so if we know the measure of one interior angle, if we take the total of the interior angles divided by the number of angles, we can write an equation then and solve for n. So to solve this equation for n, the first thing I'm going to do is multiply, since I want to get this n out of the denominator, so I'm going to multiply both sides by n. And so I would have 135n is equal to n minus 2 times 180. And then let's go ahead and get rid of the parentheses on the left side. I'm going to distribute. So I would have 180n minus 360. And then we've got an n term on both sides, so let's subtract 180n from both sides. And when we do, we would get negative 45n is equal to negative 360. Let's divide both sides by negative 45, and our answer turns out to be n is 8 sides. Okay, what we're going to do now is we're going to switch gears, and we're going to change from talking about interior angles of a polygon to exterior angles. And I just want to remind you of what an exterior angle of a polygon is. If I extend the side of a polygon, then we are always going to create what's called an exterior angle. So if we look at these polygons and we extend, okay, the sides of the polygons and create these exterior angles, one exterior angle at each vertex, we can start examining what's going on. So in each of the following diagrams, the exterior angles, one at each vertex, are labeled. Find the sum of the exterior angles of each polygon. Well, in this first example, if we were to add 120 plus 100 plus 140, that total, well, I just want to write it down so you are going to see where this number comes from. If I take 120 plus 140 plus 100, add those together, we get a total of 360 degrees. In this next example, if I take 105 plus 40 plus another 105 plus 110, add that up, we get 360 degrees again. That's interesting. How about this one? If I add all 5 of these exterior angles, so that would be 65 plus 111 plus 50 plus 36 plus 98, total that, it again turns out to be 360 degrees. So each time we did this, each time we added the measures of the exterior angles, one at each vertex, we got 360 every time. So that leads us to what's called the oops, there's a typo there. I am so sorry. That is supposed to say the exterior angles sum theorem. I must have copied and pasted. Would you please fix that? So the exterior angle sum theorem says the following. The sum of the measures of the exterior angles of a convex polygon, one at each vertex, is always, always, always going to be 360 degrees, okay? So unlike the interior angles, where the sum of the interior angles varies with the number of sides, that's not true for exterior angles. It doesn't matter whether a polygon has 3 sides or 30 sides or 300 sides. If we take the sum of the measures of the exterior angles of a convex polygon, one at each vertex, that total is always going to be 360. So we can use that exterior angle sum theorem for this example 6, where it says write an equation and solve for x. Well, you can see that what we have here is we have exterior angles, don't we? One at each vertex. Okay, well, these, I shouldn't be marking them congruent, but I just wanted to point out that they are exterior angles. So to find x, what we can do is we can add these measures together, and then since they are exterior angles, we're going to know that they're going to total 360. So I'm just going to start with one angle. I'm going to start with the 2x minus 5, okay, plus the next exterior angle plus 5x plus 2x plus 6x minus 5 plus 3x plus 10. I think I have all of them. And when I total those together, that's going to total 360 degrees. All right, so gathering like terms, I'd end up with, let's see, 18x when I divide all my x terms, and when I divide the constant terms, negative 5 and positive 10 zeros out. So we get 18x is equal to 360. Divide both sides by 18, and x is 20. Now at this point we're done because the directions said solve for x. All we had to do is solve for x here. If we were asked to find the measures of these exterior angles, we would just have to go back and plug 20 in wherever we saw x. Okay? All right, the next example says find the measure of each exterior angle of a regular dodecagon. Well, if you need to, turn the page and you can see that a dodecagon is a polygon that has 12 sides, okay? Now, if it is a regular dodecagon, that means each exterior angle would be the same. So if we're going to find the measure, well, I guess I should back up. Each interior angle is the same, and then since the exterior angles would be their supplements, each exterior angle would be the same as well. So to find the measure of each exterior angle of a regular dodecagon, we know that all 12 of those exterior angles total 360. So all we need to do is take 360, divide it evenly among the 12 exterior angles, and we get that each exterior angle measures 30 degrees. And now let's begin the second part of our lesson where we're going to be talking about parallelograms. So let's start with the definition of a parallelogram. A quadrilateral is a parallelogram if and only if both pairs of opposite sides are, this shouldn't surprise you, both pairs of opposite sides are parallel. That's where we get the name parallelogram. So first of all, know that a parallelogram always has four sides. It's always going to be a quadrilateral, and opposite sides will always be parallel. So from now on, we can always justify that opposite sides of a parallelogram are parallel by using this definition of parallelograms. So now what we're going to do is we're going to be looking at some theorems involving parallelograms, and the first one says the following. If a quadrilateral is a parallelogram, then its opposite sides are not only are they parallel, we already know that from the definition, but also opposite sides are going to be congruent. Okay, so in terms of this diagram, here we have a parallelogram. You can see the markings, so we can see that opposite sides are parallel. So we know this is a parallelogram. Well, what this theorem tells us is not only are these opposite sides parallel, but the opposite sides are also congruent. So if JKL is a parallelogram, then we can say that JK is parallel to ML. So side JK is parallel to ML. And we also know that the other pair of sides, JM, is parallel to KM. So segment JM is parallel to KL. I think I said KM a minute ago. Sorry about that. Okay, our second theorem says the following. If a quadrilateral is a parallelogram, not only are its opposite sides congruent, but also its opposite angles are going to be congruent. Okay, so given this parallelogram, JKLM, if we're assuming that JKLM is a parallelogram, then we can conclude that opposite angles like J and L are congruent. So we can say that angle J is congruent to angle angle L. Let me fix that. Angle J is congruent to angle L. And then also the other pair of opposite angles, K and M, are also congruent. So we can say that angle K is also congruent to angle M. Okay? Our third theorem that has to do with parallelograms says the following. If a quadrilateral is a parallelogram, then its consecutive angles are, before I fill in the blank, let's see if we can recall. Remember, if this is a parallelogram, let me mark opposite sides parallel. If this is a parallelogram, then for example, angles J and M would be consecutive angles. And remember, when parallel lines are cut by a transversal, consecutive angles, or at that point we called them same side interior angles, they weren't congruent, but they were supplementary. All right, so if we're assuming that JKLM is a parallelogram, then we can conclude that any pair of these any pair of these consecutive angles like angle J and angle M, whose measures are X and Y respectively, we know that those two angles are supplementary, or J and K are supplementary, or K and L, or L and M. So in any of those cases, if we assume that JKLM is a parallelogram, we can conclude that X plus Y equals 180 degrees. Those consecutive or same side interior angles are supplementary. And then our next theorem about parallelograms says the following. If a quadrilateral is a parallelogram with one right angle, okay, like in this case we have this quadrilateral that has one right angle. Let's think about this. if same side or if consecutive angles are supplementary and if opposite angles are congruent, we can pretty quickly prove that if one of those angles is a right angle, all four angles have to be a right angle. So if a quadrilateral is a parallelogram with one right angle, then it has four right angles. Okay, so let's write that theorem in terms of this picture. If JKLM is a parallelogram and angle J is a right angle, if we're assuming all of that, then we can conclude that the other three angles are also right angles. Angle K, angle L, and angle M are also right angles. Okay, the next two theorems have to do with specifically the diagonals of a parallelogram. Okay. By the way, we will be proving these theorems as we go along. Of these two, we're going to prove the second one, but let's look at this first one, this first theorem that has to do with the diagonals of a parallelogram. It says the following: if a quadrilateral is a parallelogram, then its diagonals will always bisect each other. So what does that mean? That means that the two diagonals will hit each other at each other's midpoints. Okay, so in terms of this diagram, if ABCD is a parallelogram, you can see how opposite pairs of sides are marked congruent. That means that the diagonals bisect each other. So let me just highlight one diagonal. Let me just highlight diagonal AC. Diagonal AC is being bisected by diagonal DB. Okay, these angles are bisecting each other. So again, that means that P is the midpoint of both of those. So if P is the midpoint, then that means that let me just mark that midpoint. If P is the midpoint, then that means each of those segments are being cut into congruent pieces. So let's start with the pink diagonal. Okay, if it's being bisected, that means that segment AP is congruent to segment PC, so we can make that conclusion that segment AP is congruent to segment PC, and likewise, if the green diagonal is being bisected, then we can conclude that segment BP is congruent to segment PD. So segment BP is congruent to segment PD. And this last theorem, which we're going to prove that has to do with the diagonals of a parallelogram, says the following: if a quadrilateral is a parallelogram, then each diagonal separates the quadrilateral into two congruent triangles. So let's go ahead and prove this, okay? And it's going to be a simple proof because we're just going to be proving that one triangle is congruent to another triangle. That's something we've done a lot this year. So let's take a look at our theorem. The hypothesis is that we have a quadrilateral that's a parallelogram. The conclusion is that each diagonal bisects or separates the quadrilateral into two congruent triangles. Now, there would be two diagonals, so we're only going to prove it for one diagonal. We could write a second proof for the other diagonal AC, and it would be similar. So if we have this diagonal BD, and have a parallelogram, we have this diagonal BD, what we're going to do is we're going to show that the one triangle, why don't I shade them? Why don't I make this triangle yellow? Let's get this yellow triangle congruent to this blue triangle. Okay, so how can we go about doing that? Well, first of all, we're assuming that we have a parallelogram, right? So by definition, that means that opposite sides are going to be parallel. So let's mark those opposite sides parallel. And so what we have some parallel lines that are being cut by a transversal. So let's take a look at, let me grab another highlighter. How about green? Let's make these green sides, okay? And I'm going to make the transversal, I need another color. How about, I guess I'll just make it red, okay? So if we look at these green lines and this red transversal, we can see that we have a pair of congruent angles right here and right here, okay? Because when parallel lines are cut by a transversal, alternate interior angles are congruent, okay? So now, let's see. I think I can get some more colors maybe. Well, okay, let's make AD and BD. Look at these blue parallel lines, and again, look at the pink transversal. So when we have parallel lines cut by a transversal, again, alternating interior angles are congruent. So I can mark this angle congruent to this angle, okay? So we can see that the two triangles, the yellow triangle and the blue triangle, there's two pairs of congruent angles. Also, the two triangles share a side, so we're going to see that by angle, side, angle, these two triangles are going to be congruent to each other. So let's go ahead and write that proof. So we're going to start with the fact of what we were given. We're given that we're given the information in the hypothesis that we have a quadrilateral that's a parallelogram. So we're going to say that quadrilateral ABCD, quadrilateral ABCD is a parallelogram. And then we're going to prove the conclusion, which is that the diagonal separates the quadrilateral into two congruent triangles. So the yellow triangle, I'm going to call the yellow triangle ABD. So we're going to prove that triangle ABD is congruent to triangle. Well, I need to name the blue one so that corresponding parts match up. A has no arc, so I'm going to name C first. So triangle C. And then, let's see, B has one arc, so I'm going to name D next. And then finally, let's see, D in the yellow triangle has two arcs, so that would correspond to B in the blue triangle, which has two arcs. So that's what we're going to prove is that those two triangles are congruent. All right, so step one in our proof, let's go ahead and start with the given, and that is that ABCD is a, now often we use a symbol for the word parallelogram, so we can just sketch one. So we're going to assume that ABCD is a parallelogram, so that's our given information. We're assuming that to be true. Okay, and so the next thing we're going to do is let's talk about the two pairs of congruent angles. And to make it simpler, let's number them. So I'm going to call this one angle 1, this one angle 2, and then, gosh, this diagram's getting kind of sloppy. It's called this one angle 3 and this one angle 4. So we're going to go ahead and say that angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. They have the same reason, and that reason is that when parallel lines are cut by a transversal, alternate interior angles are congruent. So here's how we wrote that. We just said parallel lines. Assuming we have a transversal, we can conclude that alternate interior angles are congruent. All right? So if we were keeping track, we'd have a side and, not a side, excuse me, we'd have an angle and another angle, okay? And then remember we talked about the fact that the yellow triangle and the blue triangle share a side that's congruent to itself. So we can say in step 3 that segment BD is congruent to itself and justify that. Oops, that should be a 2 right there. Sorry about that. Change that to 2. And we'll just justify that with the reflexive property of congruence that says every segment is congruent to itself. Okay, so that gives us a side. So we have two angles and one side. If you look at one of the, let's just look at this yellow triangle, we can see that it would be two angles on the included side. So we can say in step 4 that that triangle ABD is congruent to triangle CDB, and our reason is angle side angle implies congruent triangles. All right, and then let's finish up with a couple of quick examples. Sorry, this lesson has gotten a little bit long. So example 8 says the following: given that QRST is a parallelogram, find the values of x and y and z. So if this is a parallelogram, remember all those theorems we listed on the last page we can use to help us solve this problem. So let's start with the fact that if this is a parallelogram, that means that this segment QT and this segment RS, not only are they parallel, but they're also congruent. And if they are congruent, that means their measures are equal. So we can say that, that 5x is equal to 27, okay? Dividing both sides by 5, we get that x is equal to 27/5, okay? So we have found x. Now let's talk about how we can find y. Well, if you look at, let me see, let me highlight this diagonal. Remember, the diagonals of a parallelogram bisect each other, so that means that this is a midpoint, okay? And so this green diagonal is being cut into two congruent pieces. So I can say that 2y minus 5 is equal to y plus 4. So we'll do that, use that equation to solve for y. So I'm going to say that 2y minus 5 is equal to y plus 4. So solving for y, let's see, I'm going to subtract a y from both sides and add 5 to both sides. We get that y is equal to 9. And then last but not least, let's find the value of z. Well, let's see. Z, this is a parallelogram, right? So that means that opposite sides are parallel. So I've got these parallel sides and I have a transversal, okay? And when parallel lines are cut by a transversal, we know that alternate interior angles are congruent. So that means that 3z is congruent to 33. So that's the equation we'll use. We're going to say that 3z is equal to 33. So therefore, z is equal to 11. All right. And then last but not least, let's take a look at example 9. It says, find the value of x and y given that the quadrilateral is a parallelogram. So if this is a parallelogram, that means opposite sides are parallel. All right. So if these sides are parallel, mark them parallel, okay, then remember, same side interior angles are supplementary, or, well, we could either call them same side interior angles or we could call them consecutive angles. So if they're supplementary, that means their measures total 180. So 4x plus 2x, let's see, 4x plus 2x minus 6 is going to total 180. So 6x minus 6 is 180. So 6x is equal to 186. And if we divide both sides by 6, x turns out to be 31. All right. And then finally, to find y, okay, if this is a parallelogram, then these yellow sides, not only are they parallel, but they're also congruent, which means their measures are equal. So we can say that y plus 8 is equal to 5y. All right, so I'm going to subtract a y from both sides and get that 8 is equal to 4y. Divide both sides by 4, so y then is equal to 2. All right, so if you have any questions about these notes, be sure and ask me in class. We'll be doing some problems in class, and I will see you then.